air and combustion, and we start with composition of air. The air is a mixture of gases, dust, and water vapor. The amount of vapor varies depending on temperature. The gases in the atmosphere include nitrogen constituting 78.1%, oxygen constituting 20.9%, carbon dioxide constituting 0.03%, and noble gases make up the 0.97% that remains. The amount of dust is variable. For example, in industrial places, other gases may be present such as sulfur dioxide and nitrogen dioxide. Now, oxygen is the component of the atmospheric gases that support combustion. For example, in an experiment, if a candle is covered with a gas jar and burns over a solution of sodium hydroxide or water, the candle goes off after some time and the level of the liquid in the jar rises. Now, this shows that the fraction of air in the jar that supports combustion has been used up. Now, this is the setup we are talking about. So we have that tray there with water, and then we have a candle placed on it. We then have a gas jar that we are going to cover the candle with. But first we are going to light the candle and we let the candle burn while covered. So we light the candle first. There we have it. And then we are going to use the jar to cover the candle. So we have it there. And we carefully cover the candle. And note the level of the water in the jar. The candle burns, continues to burn, and after some time the candle will go off. And what is seen is that the level of water in the jar will rise to occupy the space left by the component of the air that has been used up. Now, if the experiment is closely monitored and the height of the water rising is noted, it will be shown that the percentage change is close to 20.9%, and this means that the part of the air that supports combustion is actually oxygen. It is important to mention here that oxygen does not burn, it only supports combustion. Now, the same conclusion will be drawn when a fixed volume of air is passed over heated copper. The red-brown copper metal, when heated in air, turns black, and the black solid is copper oxide, and the reaction that occurs is represented by equation shown on your screen. Now, the next component of the atmospheric gases is carbon dioxide. The presence of carbon dioxide in air can be tested by bubbling air through lime water, that is calcium hydroxide. A white precipitate is formed, and this is an indicator of carbon dioxide's presence. Now, for example, the lady on your screen will generate carbon dioxide by reacting an acid with a carbonate. It will generate carbon dioxide. So she adds a certain amount of hydrochloric acid into a boiling tube or a test tube, and then adds a spatula of a carbonate. Carbon dioxide is generated in a reaction between an acid and a carbonate. So she cocks that test tube, and then in another test tube she puts lime water, that is calcium hydroxide, that will be used to test the presence of carbon dioxide. Now she connects the two test tubes using a delivery tube. She'll connect them, and the carbon dioxide generated in the first test tube is bubbled through the lime water in the second test tube, and after some time, with slight warming, you see that a white precipitate is formed on the lime water. There you have the white precipitate, and it confirms that carbon dioxide is present. This is the confirmatory test for carbon dioxide. We then look at water in the atmosphere or water in the air. And water in the air can be tested by passing air over anhydrous calcium chloride. The solid absorbs water from the air, becoming wet or form a solution if the amount of water is sufficient. Such substances that absorb moisture from air to become solutions are called deliquescent substances. Next, we look at fractional distillation of liquid air. Now, we have seen that mixtures can be separated, and air being one of them is no exception. The process of obtaining the different components of the atmospheric air can be summarized as follows. The first step is purification, and purification is done by passing the air through filters to remove dust. The purified air is then bubbled through concentrated sodium hydroxide to remove carbon dioxide. The remaining air is then cooled to negative 25 degrees Celsius to remove water vapor. The water-free air is then compressed to a pressure of 200 atmospheres and allowed to expand, and this is repeated several times. Now, this compression and expansion of air cools it to negative 200 degrees Celsius, becoming liquid. The liquefied air contains mainly oxygen, nitrogen, and argon, all of which have different boiling points. The mixture is then subjected to fractional distillation, and the parts distill out in the order: nitrogen will come out first, followed by argon, and then oxygen. Why? Because nitrogen has the lowest boiling point of negative 196 degrees Celsius. Argon follows with negative 186 degrees Celsius, and oxygen has the highest boiling point at negative 183 degrees Celsius. All that information is summarized on the flowchart that is on your screen, and you can see from that flowchart the air being passed through filters to remove dust. We then have the dust-free air being bubbled through sodium hydroxide. The air that comes out is free of carbon dioxide. Now, this air is then taken to a cooler. It's cooled to negative 25 degrees Celsius, and water vapor is removed. The dry air is then taken into a compression chamber. It is compressed to a pressure of negative 200 degrees Celsius. Compression and expansion to cool to negative 200 degrees Celsius, and then it is taken to a fractionating column. There is a fractionating chamber where fractional distillation is done, and the air comes out. Elements of the air come out in the order of nitrogen, followed by argon, and then oxygen comes out last. So that is fractional distillation of liquefied air. Now we turn and look at rusting. Now, you have always seen the once shiny iron sheet roofing turn into brown dull color. Many other metals also change their surface color after some time due to chemical reactions, and this is called corrosion. Corrosion of iron due to reaction with atmospheric oxygen in the presence of moisture is called rusting. Rust is the dull brown coating on the surface of iron. Now, because it is porous, rust allows air and moisture to penetrate through, causing more rusting into the deep metal until all the metal has rusted. Rusting reduces the durability and value of the material. What are the conditions for rusting? Now, in the following experiment, we can be able to deduce the conditions necessary for rusting. We shall have 5 test tubes, and in them we shall put iron nails, but then we shall subject them to different conditions. In test tube 1, the iron nails are put in tap water. In test tube 2, iron nails are put in boiled water, and then a layer of oil is added at the top. In the third test tube 3, the iron nails are put in an empty test tube, and anhydrous calcium chloride is placed in the test tube, and it is then cocked. In the test tube number 4, test tube 4, the nails are put in salty tap water, and in the last test tube 5, the nails will be placed in an open test tube with no water. Now the nails are left for a few days, and then we come and make observations. Now the important thing to observe is which nails rusted, which rusted fastest, if at all they did rust. Few days, the following observations will be made: that nails in test tube 1, 4, and 5 rusted, while those in test tubes 2 and 3 did not. Now the explanation for this can be given as follows. In test tube 2, boiled water has no oxygen. Boiling expelled the oxygen that had dissolved in the water. The layer of oil that was added prevented atmospheric oxygen from dissolving back. In test tube 3, the oxygen is present, but there is no moisture. The anhydrous calcium chloride absorbs all the moisture, leaving the environment very dry. The cork prevents further entry of moisture from the atmosphere. Now, after 3 days, most rusting would have occurred in test tube 4, followed by 1 and then 5. Again, what is the explanation? Tap water contains dissolved oxygen, which reacts with iron in the presence of the water, and hence rusting occurred. For tube 5, atmospheric air contains oxygen, which reacted with the iron in the presence of atmospheric moisture, and hence rusting occurred as well. Rusting was more intense in test tube 4. Why? Because of the salt. Salt is not a condition for rusting, but only accelerates the process. This is why cars would rust faster at the coast compared to interior regions, due to presence of salty environment. High temperature also accelerate the rate of rusting. Now, in summary, rust is hydrated iron 3 oxide. The reactions that occur can be represented as follows. Iron reacts with oxygen to form iron 3 oxide. It is this iron 3 oxide that then combines with water or moisture to form hydrated iron 3 oxide. The conditions necessary for rusting are presence of oxygen and moisture. High temperature and acidic environment or salty environment accelerate the process of rusting. So how can one prevent rusting? Now, the idea in prevention of rusting is to block the contact between oxygen and the iron surface. The methods include the following. The first one is coating the iron with other metals through galvanization or electroplating. You can also put metal surface. Alloying is also done, and alloying is mixing iron with other metals to produce a substance that doesn't rust. Oiling and greasing can also be done to block the entry of moisture and air. Now we look at oxygen in greater details, and oxygen is a component of the atmospheric gases. Its chemical symbol is a capital O. The atoms of oxygen do not exist independently, but two of them combine to form an oxygen molecule. Oxygen is also found combined in compounds such as oxides, sulfates, carbonates, nitrates, nitrites, and others. It is the most active component of air. Laboratory preparation of oxygen. Now, in the lab, oxygen gas is prepared by decomposition of hydrogen peroxide. Hydrogen peroxide decomposes slowly to produce oxygen and water, but to speed up the decomposition, we add manganese 4 oxide, which acts as a catalyst. Remember, a catalyst is not a reactant, rather it only speeds up the reaction. So there we have the hydrogen peroxide. It's a colorless and highly volatile liquid. It decomposes naturally into oxygen and water. So in the preparation, you can see there the manganese 4 oxide already present there and in water. The next thing we are going to do is add hydrogen peroxide in the water, and the manganese 4 oxide will catalyze the reaction to generate oxygen, the decomposition of the hydrogen peroxide. The oxygen is carried through the delivery tube to the gas jar, and you can see the water being displaced downwards. There you have your oxygen in the gas jar as displaced water. Now, the equation for that reaction can be shown here. Hydrogen peroxide decomposing under the catalyst of manganese 4 oxide to form oxygen and water. Now, the confirmatory test for presence of oxygen is that oxygen relights or rekindles a glowing splint. You can take a look at that, what the lady is doing on your screen. Having said that, we now look at how substances burn in air and oxygen at large. And we start with metals. Now, metals such as sodium, calcium, magnesium, and so on will burn at different rates in air and in oxygen to give products with different properties. All of them burn faster in oxygen. In air, nitrogen slows down the rate of burning. When metal burns in air, they form metal oxides. Sodium. Sodium in air burns with a yellow-orange flame to produce a few sparks. In oxygen, it burns vigorously with a yellow-orange flame to produce white solid, which is sodium oxide and sodium nitride. The product is soluble in water to form an alkaline solution, and a gas is evolved. There you have the burning of sodium. As for calcium, it burns in air with a brick red glow. In oxygen, it burns vigorously with a red flame, and the product is calcium oxide and calcium nitride. Calcium nitride is a white solid, slightly soluble to form an alkaline solution with evolution of a gas. Let's look at industrial combustion of calcium. Next is magnesium, and magnesium burns in air brightly with a white blinding flame. In oxygen, it burns more brightly with a white glaring flame to produce white powder of magnesium oxide and magnesium nitride. Magnesium oxide is slightly soluble to form an alkaline solution with evolution of a gas. Let's look at combustion of magnesium in air. Please note the glaring or blinding flame of magnesium as it burns. And then we have iron, and in air iron glows red with few sparks. In oxygen it glows more brightly and sparks are produced, the product being iron 3 oxide, which is a red brown solid which is insoluble in water. And then we have copper, and in air there is no visible or apparent burning. The surface only turns black. In oxygen, copper burns with a blue flame and the surface turns black. The product is copper 2 oxide, which is a black solid which is insoluble. Now, the reactive metals, that is sodium, calcium, and magnesium, when burnt in air, reacted with nitrogen to form nitrides. When dissolved in water, the nitride react with water and ammonia gas is evolved. The other metals are less reactive and do not react with atmospheric nitrogen. The reactions of substances with oxygen is termed as oxidation. The substance is said to be oxidized. Copper was the least reactive. Mercury, silver, and gold are less reactive than copper actually. And on your screen is a reactivity series of a list of selected metals. And next is burning of nonmetals. Common nonmetals include carbon, sulfur, and phosphorus. We start with sulfur, and sulfur burns in oxygen with a blue flame to give a gaseous product called sulfur 4 oxide. Take a look at that. Now the reaction can be represented by the equation on your screen: sulfur reacting with oxygen to form sulfur 4 oxide. Now this gas product has an irritating choking smell, and when water is added, the solution is acidic and turns a litmus paper red. Sulfur 4 oxide plus water forms sulfurous acid. On its part, carbon burns in oxygen with a yellow flame to give white fumes of carbon 4 oxide. Take a look at that. When water is added, the solution turns a litmus paper red. The reaction can be represented by the equation on your screen: carbon reacting with oxygen to form carbon 4 oxide. The carbon 4 oxide dissolves in water to form carbonic acid. In limited oxygen, carbon 2 oxide is formed, that is carbon plus limited amount of oxygen to form carbon 2 oxide, otherwise commonly known as carbon monoxide. On its part, phosphorus burns in oxygen with white flame to form white fumes of phosphorus 3 oxide and phosphorus 5 oxide in limited and excess oxygen respectively. Again, take a look at that. And this can be represented by the following equation: phosphorus plus oxygen in limited supply will form phosphorus 3 oxide. Phosphorus again with oxygen in excess supply or in plenty will form phosphorus 5 oxide. And again, the solution of this is acidic. Now, some nonmetal oxides are neutral, including carbon 2 oxide and hydrogen oxide. And next we look at competition for combined oxygen. And if an oxide is reacted with another element that is higher in the reactivity series, the more reactive element displaces oxygen from the oxide. Take for instance a reaction between copper 2 oxide and carbon. Carbon is more reactive than copper and it will displace oxygen from copper 2 oxide to form carbon 4 oxide and copper.
In this experiment, we heat together a mixture of black carbon powder and black copper oxide. The gas evolved is passed into a solution of calcium hydroxide, that is lime water. Notice the white precipitate of calcium carbonate, formed as the evolved gas passes through the lime water. This shows that carbon dioxide is produced. As the black mixture is heated, the copper oxide is reduced to red copper by the carbon, which is itself being oxidized to carbon dioxide. After the tube has cooled, we can see the copper that has been formed at the bottom of the tube. When we tip out the mixture at the conclusion of the experiment, we can see that it is now red-brown due to the copper produced by the reduction of copper oxide.
That is shown by the equation on your screen. Carbon plus copper 2 oxide forms carbon 4 oxide plus copper metal. We say that carbon has been oxidized while copper 2 oxide has been reduced. The reverse cannot happen in that copper cannot displace oxygen from carbon 4 oxide. Why? Because carbon is more reactive than copper. In summary, a metal higher in the reactivity series displaces oxygen from the oxides of metals lower in the reactivity series. That is to say, calcium when reacted with copper 2 oxide, it will form calcium oxide plus copper, calcium taking the oxygen from copper 2 oxide. Sodium plus iron 3 oxide will form sodium oxide and iron. Why? Because sodium is higher in the reactivity series compared to iron. Calcium will displace oxygen from magnesium oxide to form calcium oxide and magnesium, amongst many other reactions. Now we look at pollution, and the emission of gases such as carbon 4 oxide and sulfur 4 oxide and also phosphorus 5 oxide cause atmospheric pollution. The gas mainly come from combustion of fossil fuels. For instance, sulfur 4 oxide dissolves in rainwater and is converted to sulfurous acid, forming acid rain. This rain is responsible for corrosion of iron sheets, zinc roofings, buildings, as well as destruction of plants and aquatic lives. And finally, we look at the uses of oxygen. And air enriched with oxygen is used in hospitals by patients with breathing difficulties. Oxygen is used by mountain climbers and deep sea divers when mixed with helium. Burning fuels in propelling rockets is also a use of oxygen. Oxygen is also used in welding and cutting of metals when mixed with acetylene. Oxygen is also used in the removal of impurities during steel mining. And finally, it's used as a reactant in fuel cells.
Choose a path, choose a direction, choose your day, choose your hours, choose to network, choose a strategy, choose to create, choose your media, choose to care, Choose to inspire. Choose to listen. Choose to learn. Choose to train. Choose to compete. Newcastle College. Why choose anywhere else?